வணக்கம் நேயர்களே. நம்ம அடுத்த பகுதியாக சாலிட்ஸ்ல ஏற்கனவே 4 பகுதி பார்த்திருக்கோம். சாலிட்ஸ் பார்ட் 1, சாலிட்ஸ் பார்ட் 2, இம்பார்ட்டன்ட் ஃபார்முலா இன் சாலிட்ஸ், நீட் ப்ராப்ளம்ஸ் பார்த்தோம். அதுக்கப்புறம் என்சிஆர்டி ப்ராப்ளம் பார்க்க போறோம். இப்ப நம்ம என்ன பார்க்கிறோம் அப்படின்னாக்க, சாலிட்ஸ் அப்படின்றதுல என்னென்ன கான்செப்ட்ல எப்படி எல்லாம் ப்ராப்ளங்களுக்கான ஃபார்முலாஸை டிரைவ் பண்ணலாம்னு பார்க்கலாம். இது ஒரு வீடியோ பிரசன்டேஷன்ஸ் பாருங்க, கடைசியா பார்க்கலாம். இந்த என்ரிச்ல நம்ம என்ன அப்ரோச்சஸ் வச்சிருக்கோம் அப்படின்னாக்க, முதல்ல என்சிஆர்டி புக்கை வரி வரியா படிச்சு ஒரு கிளாஸ் நோட்ஸ் கொடுக்குறோம். இந்த கிளாஸ் நோட்ஸை ஹேண்ட் ரிட்டன் ரைட்டப்பா நீங்க என்ரிச் எஜுகேஷன் ஃபவுண்டேஷனுக்கு மெயில் பண்ணி வாங்கிக்கலாம், அல்லது அவங்களுக்கு இருக்கக்கூடிய ஃபேஸ்புக்ல அவங்க என்ன செய்வாங்கன்னாக்க அதை பப்ளிஷைஸ் பண்ணியிருப்பாங்க, அதை நீங்க எடுத்து பயன்படுத்திக்கலாம். பாயிண்ட் நம்பர் 1. பாயிண்ட் நம்பர் 2, அந்த கான்செப்டை என்சிஆர்டி போட்டிருக்கக்கூடிய எக்ஸாம் ஃபியர் வீடியோ, மிக மிக அற்புதமான ஒரு வேலையை என்சிஆர்டி செஞ்சிருக்காங்க. எக்ஸாம் ஃபியர் வீடியோ அப்படின்றது பரீட்சையை பற்றிய பயத்தை நீக்கிறதுக்காக கான்செப்ட் எல்லாத்தையும் சின்ன சின்னதா வீடியோஸா கன்வெர்ட் பண்ணி 10 அல்லது 15 வீடியோஸா போட்டிருக்காங்க. அதை பேஸ் பண்ணியும் என்சிஆர்டி புக்கை பேஸ் பண்ணியும் என்சிஆர்டியினுடைய சிலபஸ் அப்படியே ஃபாலோ பண்ணக்கூடிய சிபிஎஸ்இனுடைய மிக பிரபலமான லக்ஷ்மி பப்ளிகேஷன், பிரதீப், எஸ்எல் அரோரா போன்ற புத்தகங்களிலிருந்து தொகுக்கப்பட்ட வினாக்களின் தொகுப்பை பத்தி நம்ம கிளாஸ் நோட்ஸா கொடுத்துருக்கோம். சரியா? அதை தவிர எக்ஸாம் ஃபியர் வீடியோவில் இருக்கிற மாதிரியே அனிமேட் பண்ண முடியல நம்மளால. பட் ஆனா என்ன செஞ்சிருக்கோம் அப்படின்னாக்க, பிபிடியா கன்வெர்ட் பண்ணி உங்க முன்னாடி பிரசன்ட் பண்ணிருக்கோம். இதை தவிர உலக அளவுல சில பிரபலமான நிறுவனங்கள் என்ன செய்திருக்கின்றது என்றால், இதுல என்னென்ன டைப் ஆஃப் ப்ராப்ளம் வரலான்றதை கேட்டிருக்கோம். அதை இப்ப நமக்கு பார்க்க போறோம். இதை ஒட்டி என்சிஆர்டியுடைய புத்தகத்தில் இருக்கக்கூடிய வினாக்களுக்கு பதிலளிச்சிருக்கோம், நீட் வினாக்களுக்கு பதிலளிச்சிருக்கோம். கூடிய மட்டும் இந்த சாப்டர் உங்களுக்கு தரவு பண்ணணும்ன்றதான் எங்களுடைய நோக்கம். இப்போ முதல் வீடியோ பார்க்கிறோம், ஸ்ட்ரெஸ் ஸ்ட்ரெயின் பேசிஸ். மிக அற்புதமான ஒரு வீடியோ இது. இந்த வீடியோ பார்க்கலாம்.
Okay, welcome to ilectureonline. In this next set of videos, we're going to talk about the stress and strain of materials, and we're going to start out with the very basic concept of what that really means. So first of all, we're going to define the term stress. Stress on a material is simply the force divided by the cross-sectional area over which it is applied. For example, if you have a beam like this and you push down on it with a certain amount of force and the beam has a certain amount of cross-sectional area, the stress is simply expressed in terms of the ratio of the force divided by the area. Now notice that if we have a larger cross-sectional area, like a much bigger beam like that, and we apply the same force, but the area is different, then the material will experience a different amount of stress. And you can see that if the area is larger, a larger area makes this a smaller quantity, that means there is less stress. So this beam is experiencing less stress than this beam, even though the amount of force applied to the beam is exactly the same. So you can see how stress is actually a function of both the force applied and the cross-sectional area of the material. So here we can see that there's a large amount of stress applied to this material, this beam right here, and here is a smaller amount of stress applied to the beam. The second part of the relationship between stress and strain is the second portion, namely strain. And the definition of strain is that it's a ratio of how much the material deforms, so let's call that deformation. In the case of a linear element here, like a linear beam, if we push down on the beam, we may make the beam a little shorter. We're deforming it by making it shorter, and that's called deformation. And if we find the amount by which it deforms divided by the original size of the object, so for example, this may be the deformation, the reduction in the length of the beam after we apply a certain amount of force on it. So let's assume we apply a force, and therefore because of the force applied, we actually make the beam shorter. So we deform the beam, and the ratio of the amount of the deformation divided by the original shape, which would be in this case the original length, is what we call the strain. In this case, if the deformation is large, we expect a large strain. In other cases, the beam may only, under maybe applying the same amount of force, may not experience the same amount of deformation. In this case, the deformation is relatively small, so therefore the ratio of the deformation divided by the original length is much smaller, and so therefore we can say that there's a small amount of strain on this beam and a large amount of strain on that beam. So why would that be? Why would some beams have a large strain when a certain amount of force is applied, and other beams will have a very small strain? Well, that has to do with the strength of the material of the beam. And so let's imagine, for example, that this is a beam made out of steel. And of course, if we take a look at the molecular level, if we zoom into a very small portion on the beam, and we take a look with a very powerful microscope, and we see that this beam is made up of atoms, and those atoms are usually, in a solid object of course, in a crystalline structure of some sort. They're usually locked into a certain structure. They do vibrate because of the thermal agitation, but they're all locked into one another. And the atoms are spaced just exactly right so that the forces between them is balanced out, and so they take up a certain amount of space between them, and they have a certain amount of space between each atom. So now what happens when you apply a force on a beam like that? Well, what you're trying to do is you're trying to push the molecules closer together. Now, if the molecules can easily be forced closer together, then you'll experience a large amount of strain. If the molecules experience a lot of force so that there's not a lot of room for them to be compressed together, then you experience a much smaller strain. For example, metals tend to be of the type where you have very, very small amount of deformation. You take a steel beam, you try to push on it, you're not going to make it much smaller. But if you take, for example, a beam made out of foam and you push down it, you'll see that there's a lot of strain because the molecules do not, they're not very cohesive. There's not a lot of as much force between them to hold them in shape. So that's where you find a different amount of strain. Now what we tend to do with this, the concept of stress and strain, and by the way, one more thing I wanted to point out, notice that stress is force divided by area, and that would be newtons per square meter, and that is also those are also the units of pressure. So it turns out that stress is very synonymous with pressure, and so again, pressure is force per unit area. Large amount of force, small area, a lot of pressure. Small amount of force, large area, small amount of pressure. So there's a lot of similarity between pressure and stress. Now, if we find the ratio between stress and strain, so we take stress, which is force divided by area, and divided by the strain, that ratio gives us an indication of what kind of material we're dealing with. For example, if we apply a small amount of, let's say we apply a large amount of stress, and there's a small amount of strain. In other words, just a little bit of deformation when we really push down on the material. If that ratio is large, what kind of material are we dealing with? We're dealing with a very strong material, a material that it does not deform very easily. And so this then would indicate a certain amount of property relative to the material, and we'll talk about what that is in just a moment. On the other hand, let's say we apply not a lot of stress, not a lot of force, and the strain is considerable so that this fraction is large, so that fraction is small, because that's what it says right here. So again, small amount of stress, a considerable amount of strain, so the ratio is very small, and we're dealing with a very weak material, a material that very easily compresses. So here we're dealing with a weak material. Now, since this ratio of stress divided by the strain, again, stress is kind of like pressure, how much force we apply to it per unit area, and we divide that by the strain, how much deformation is relative to the original shape of the object. When we take that ratio, if that ratio is large, we're dealing with a strong material. If that ratio is small, we're dealing with a weak material. And so it turns out that we call this ratio something. We call that the Young's modulus. So the Young's modulus is an indication of how strong or how weak the material is. And strong or weak, we're talking about in terms of how much it can resist deformation under stress. And so, again, we're going to talk about Young's material in a future video, in a few videos down the road, a little bit more after we get the basics out of the way. But again, notice that that ratio does give us a property of the material, and so we'll talk a little bit more about that later. But here you have your basic concept of stress and strain and how that ratio actually means something to us, and we'll take use of that in future videos.
இப்போ நம்ம ஏற்கனவே பார்த்தோம் ஸ்ட்ரெஸ் அப்படின்னா ஃபோர்ஸ் பை ஏரியா, ஸ்ட்ரெயின் அப்படின்னா டிஃபர்மேஷன் பை ஒரிஜினல் டைமென்ஷன். சேஞ்ச் இன் டைமென்ஷன் டு தி ஒரிஜினல் டைமென்ஷனுக்கு பேரு ஸ்ட்ரெயின். ஒரு பாடி ஒரு ஃபோர்ஸ்னால ஸ்ட்ரெயின் ஆறப்போ இந்த ரெண்டுக்கு இருக்கக்கூடிய ரேஷியோ சின்னதா இருந்ததுன்னா அந்த பாடியினுடைய யங்ஸ் மாடுலஸ் கம்மியா இருக்கும். சில இதுல அதிகமான ஸ்ட்ரெஸ்ஸுக்கு குறைவான ஸ்ட்ரெயின் இருந்ததுன்னா ரேஷியோ கூட இருக்கும். அதிகமான ஸ்ட்ரெஸ் கொடுத்தாலும் குறைவான ஸ்ட்ரெயின் இருக்கக்கூடிய மெட்டீரியல்னா ஸ்ட்ரென்த் மெட்டீரியல். குறைவான ஸ்ட்ரெஸ்ஸுக்கே அதிகமான ஸ்ட்ரெயின் இருந்ததுன்னா வீக் மெட்டீரியல். அப்போ ஸ்ட்ரெஸ் ஸ்ட்ரெயினுக்குள்ள இந்த ரிலேஷன் ஸ்ட்ராங் மெட்டீரியலா வீக் மெட்டீரியலான்னு கண்டுபிடிக்க யூஸ் ஆகுது. சரியா? அடுத்தது பார்க்கலாம்.
Welcome to our lecture online, and in this next video we're going to explore stress and strain a little bit more. In this case we're going to talk about what we call either tensile or compressive stress and strain. So in this case here we have a bar and we're pushing on the bar from both ends, trying to make the bar shorter. In this case we say that the bar is under compression. We're trying to compress the bar. We're trying to make the bar shorter. And so therefore when we talk about stress, we really talk about compressive stress. And again, it's the force applied on both ends. Of course, Newton's third law requires us to push with an equal amount of force on both ends. So we take the force on either end and divide it by the cross-sectional area, and that would then be the stress. Again, the stress is determined both by how much force you apply and over how big a cross-sectional area you apply it. The strain then is the deformation divided by the original size. In this case, this will be in terms of length. And so by compressing the bar, we're making the bar a little bit shorter. That's delta L. Notice when we make it shorter, we tend to use a negative because it's decreasing in length. And that would then be the original length. So that would be the ratio of the change in length over the original length, which is called the strain. And again, the ratio of the stress over the strain, when we write it like this, is F over A divided by the change in the length divided by the original length, and we can ignore the negative for a moment. Just that ratio by itself is called the Young's modulus. Now, let's take a look at our second bar. In this case, we're pulling on the bar, both ends, and pulling apart from each other. Again, those forces have to be equal, Newton's third law, because if one was bigger than the other, the bar would accelerate in one direction or in the other direction. So for the bar to stay stationary, you got to pull both directions with the same amount of force. We now say that the bar is under tension. We're pulling on the bar, we're trying to make it longer. That's called tension. And therefore, instead of calling it compressive stress, we're going to now call it tensile stress, since we're pulling on it, the bar is under tension. So tensile stress is defined exactly the same way. It's force divided by area. And the tensile strain is the deformation, in this case the length, divided by the original length. Notice here it will be a little bit longer, so delta L is therefore positive. And if we find the ratio of that, stress over strain, it doesn't matter if it's compressive stress and strain or tensile stress and strain, the ratio means exactly the same thing and still will be the Young's modulus. The vast majority of materials, if not just about all materials, they have the same ratio of stress over strain regardless if you compress it or if you stress it in the opposite direction. So compressing or put under tensile stress, you find the same ratio. So again, to illustrate that ratio, we call that Young's modulus, and we'll talk a little bit more about that in a later video. But again, understand that the size of this ratio talks about, or the size of the ratio implies the strength of the material. How easily does it resist deformation? The bigger the number, the bigger the ratio, the more it resists deformation. The smaller the number, the less it resists deformation. So as an example, we have two materials, call it aluminum and call it brass. Aluminum here has a Young's modulus of 7 times 10 to the 10th newtons per square meter. Brass has a Young's modulus of 9 times 10 to the 10th newtons per square meter. So without going into the details, because we'll do that in the next video, a couple videos from now, we just want to look at those numbers, and can you tell from looking at these numbers which material resists deformation the best? And since brass has a larger Young's module, you could say brass resists deformation better than aluminum. So putting the same amount of force on brass and aluminum, aluminum will deform a little bit more, brass will deform a little bit less. As long as the force are the same and of course the length is the same. If the length is different, of course, then of course again the ratio will still take care of itself. But I would say what's important is that we look at the compressive stress and that the force divided by the area is similar or the same for both, otherwise you can't compare them very well. But again, the ratio of the stress over the strain, you can see the result. Aluminum, not so good. Brass, a little bit better. But even though aluminum has a smaller number, that's still a really big number, and you can see you need a lot of force to cause any sort of appreciable deformation, even if it's aluminum. But that's just for comparison. That's how you look at tensile stress and compressive stress.
இப்போ நம்ம என்ன பார்த்தோம் அப்படின்னாக்க, மிக முக்கியமா ஒரு பாடி மேல ஒரு நார்மல் ஃபோர்ஸ் வந்ததுனாக்க அந்த பாடி எலாங்குவேட் ஆகலாம் அல்லது கம்ப்ரஸ் ஆகலாம். அப்ப எலாங்குவேஷன் கம்ப்ரெஷன் ஆகிறப்ப கிடைக்கக்கூடிய யங்ஸ் மாடுலஸ் என்ன டிட்டர்மின் பண்ணுதுன்னா, அந்த ப்ராப்பர்ட்டி ஆஃப் மெட்டீரியல் கம்பேர் பண்ணுது. அலுமினியம், காப்பர். ஈவன் இன் கேஸ் ஸ்டீல் எடுத்துக்கிட்டோம்னா, இந்த மூணுல ஸ்டீலை தான் கன்ஸ்ட்ரக்ஷனுக்கு பயன்படுத்துறோம், காப்பர் பயன்படுத்துறது இல்ல, அலுமினியம் சில இடத்துல பயன்படுத்துறோம். ஏன் அப்படின்னாக்க, எதுக்கு யங்ஸ் மாடுலஸ் கூடவோ அந்த மெட்டீரியலை பயன்படுத்துறோம். இதை வச்சு இப்போ இன்னொரு வீடியோ பார்க்குறோம். நம்ம ஒரு சாலிட் பிளாக்கா பீமை பண்ணாம ஐ ஷேப்ல ஒரு பீமை பண்றோம். ஏன் இந்த ஐ ஷேப்ல அந்த பீம் பண்ணப்படுது அப்படின்றத பத்தி பார்க்குறோம். This is the application of Young's modulus. Okay.
Here we're going to see a very interesting application of tensile strength and compressive strength, and tensile stress and compressive stress. So going back to the concept, here we have a beam. Let's say the beam is suspended at both ends, and beams are usually used to hold big loads so that we could put forces on them. And so let's say we apply a force to the beam, and if the force is very large, typically the beam will be, as a response, will begin to sag to some extent. Of course, I exaggerated the sag so we can see what happens. But what the result is that the atoms near the top of the beam get pushed together, and so there is a compression taking place near the top of the beam. On the other hand, on the far end of the beam, from where the force applies at the bottom end of the beam, the belly of the beam, so to speak, that part of the beam is under tension, meaning the molecules are being pulled apart. And of course, the danger is that if you apply too much force, the beam could actually begin to crack. So for example, you have a wooden beam, you apply too much force, you can actually destroy the beam. And of course, that's the purpose of the beam, is to hold a lot of weight. But if the beam starts cracking, of course, it doesn't do what it's supposed to do. So what people started realizing is that, wow, what's really the part of the beam that's really under compression and under the most compression is the top portion of the beam right here. So what I did over here is just kind of mark that off. It's this portion of the beam that's going to be under the most compression. The most force is applied to the beam, pushing the molecules together. And the bottom end of the beam is going to be under the most tension. Because of the sag of the beam, the molecules are going to be pulled apart the most at the very bottom of the beam. So those are the two portions of the beam that are the most important, and the portion in the middle is not near as important for the strength of the beam. So therefore we build what we call the I-beam. Beams that have a very wide section at the top, which is not necessarily very thick, but very wide. Then we have a single, very thin portion going down, and then we have a second portion right here, which is the bottom end, again, that is very wide, not necessarily very thick. And so what happens then is that portion now, as you put force on the beam, and you could put a lot of force on the beam right here, then this is going to be again under compression. As the beam sags, those molecules are going to be pushed together. But since there's such a large cross-sectional area, that causes therefore the ability to absorb a lot of force, so the stress will be reduced simply by the fact they have a much larger cross-sectional area here than you do over there in that part of the beam. And then likewise at the bottom of the beam, by pushing down on it, those will be under tension. Those molecules are going to be pulled apart, but again, since it's much larger cross-sectional area, the stress will be reduced because the A is much bigger than that. So we have a much smaller stress on an I-beam compared to a typical beam like that that's built like a normal beam. Now, also, this portion, the wider you make this, it has some benefits as well, but the key areas of defense against stress from putting weight on a beam are the top and the bottom portions. So what that means is if you reduce the stress, that will then cause to have less strain as well, because the ratio of these two will always equal to what we call Young's modulus, which is dependent on the property of the material. So if we make a steel beam that has a very large Young's modulus, if we reduce the stress, we will then reduce the strain as well, and it will not sag as much. So if you want a very strong structure, instead of using beams that look like this,
அப்ப நம்ம என்ன பண்றோம்னாக்க ஒரு பெரிய சாலிட் பாரை வந்து பீமா போட்டு பில்டிங்கை பாதுகாக்கிறதுக்கு பதிலா ஐ பீமை போடுறோம். இப்போ புரியுமா? சாதாரணமா பிசிக்ஸ் வந்து கான்செப்ட்ல இருந்து அப்ளிகேஷன் போய் இன்ஜினியரிங் போயிருக்கிறது பார்க்கணுமா? அப்ப இன்ஜினியரிங்ல ஏன் இந்த சப்ஜெக்டுக்கு இம்பார்ட்டன்ஸ் அப்படின்றத நீங்க தொடர்ந்து பார்க்கலாம். நன்றி, மீண்டும் சந்திக்கலாம்.